Okay, data owner, you sign every query results that the user asks. Then the data owner has to be online all the time, answer the digital signatures. And of course, conventional digital signature is no longer valid in this scenario. As I said, data, like the redacted document, they undergo transformations. If you just sign the original document using RSA signature, they will not be valid at the end after parts of it are removed. So we'll have to use some other techniques. So in this talk, we only consider two aspects of the outsourced verification problems. And one of it is verification of third-party pseudonymized document. And this is very close to redacted document. In the redaction case, text is completely removed, and we want to provide a pseudonym instead of a blackened text. A pseudonym example in this case will be, we'll say, soldiers in A division and B division have come to refer to the certain thing. And the good thing about pseudonym is it provides a better reading context for the readers, and also pseudonym can be linked. For identical words that appeared in the document, they will replaced by identical pseudonyms. Therefore, the user have a better reading context. And then another aspect that we consider is integrity verification of third-party aggregate query results. And aggregate queries include sum, max, min, count, average. And we consider privacy-preserving verification of both the correctness and the completeness of aggregate query results. I'll give more explanation in the later part of the talk. All right. For the pseudonymized model, we consider again three parties. We have a data owner who has a document, a service provider who will pseudonymize the document, and the user who queries the pseudonymized document. So the data owner will first prepare the document by signing it and provide some auxiliary information. And this is given to the service provider in a secure channel. Now, once the user requests for a pseudonymized document, the service provider will pseudonymize parts of it based on the user's permission. Now, how to determine who can access what part of the document is outside the scope of this talk. So we just say the service provider prepare a pseudonymized document according to some specifications. And then the user verify this document with the public key of the data owner. Now the user does not need to trust the service provider in this scenario. So the security requirements, we have three security requirements. One is confidentiality. That is, having seen the pseudonyms, the user cannot guess with non-negligible chance of the original context. So this is provide the secrecy of the document. The other is unforgeability. Essentially, it says service provider and any other third party cannot forge a valid signature that can be accepted by the user. And then finally, consistency is specific requirement to this scenario. Consistency basically means identical words in the document has to be replaced by identical pseudonyms. So the user will get the original context of the document. So those are the three security requirements. And then we also give a formal definition of this based on a semantic secure model, but I'm not going to talk about this in this talk. All right, so our solution is based on Merkle hash tree, and we generalize an existing redactable signature scheme by Johnson, Mona, Song, and Wagner in 2002. So here I'm going to first briefly describe their solution, and then talk about how we generalize their model to pseudonyms. So imagine you have a very simple document, just have 4 words. And each word is a subdocument, is a component of the document. Now, we want to construct a Merkle hash tree. The data owner constructs a Merkle hash tree based on the document, and then eventually sign the root hash, which will be used as a proof for the user to verify the integrity later on. The data owner uses random values when computing the Merkle hash tree. So for each component of the document, a random value is introduced, and they are hashed together with the text, and a Merkle hash tree is constructed from the bottom up. So the reason that we use this random value is to prevent a dictionary attack. Because if you omit the random value, once the user has the hash value, for example, H00, the user basically can go through all the combinations of words and then see whether they match with the hash value. So we introduce this random aspect. And then the root hash is signed by the data owner. And all these information, including the random values, are given to the service provider. So the service provider will know the original context. Will have the original text and the random values, and also the digital signatures. So for the redaction option, for example, if we want to redact fox, that means we want to remove the fox away from the document. Now, the service provider will have to do the following. We'll have to compute intermediate hash for fox, and that is H11, which is computed the concatenation of fox and its corresponding random value. And H11 is computed because when the user will have to reconstruct the Merkle hash tree later on, so without knowing fox, the user can still use H11 to reconstruct the tree and the root hash. So the redacted document, and the redaction is represented by the black square, along with the random value. Notice that for non-redacted document, random values are given to the user. For the redacted part, the random value is omitted. In place of that, the intermediate hash is given to the user. Now, for verifying this redacted document, the user will have to do the following. The central idea is to basically reconstruct the root hash from this redacted document. And for the parts that are redacted, the user does not know the leaf nodes of the tree, the user will use the intermediate hash, H11. So it's quite straightforward. And once the user gets the root hash, the signature is verified. So this is the original digital redaction signature scheme. Now we want to generalize this to consider pseudonyms. And we actually just made a very simple modification to this.